So welcome to our webinar. From Bureau Veritas, we are very pleased for your attendance. This webinar will be an opportunity to discover the key developments in the gas carrier industry. So gas carriers are part of the energy transition as they transport lower carbon fuels and help industries to reduce their greenhouse gas footprint. At the same time, they have to find themselves their path to decarbonize with different key technologies. So today for this webinar, I have the pleasure to have my colleagues from Bureau Veritas, so Carlos Guerrero, Benoit Grovel, José Esteve, and myself, who are respectively for Carlos, Global Market Leader for Gas Carrier. Benoit is Director for Gas Project within the New Building in Department, and José is the Global Market Leader for Power Barges. So a few words about Bureau Veritas. So we are Bureau Veritas Marine Offshore is part of the larger Bureau Veritas group, which has more than 400,000 clients worldwide, 82,000 employees, with a 6.2 billion euro revenue. So in the shipping market, Bureau Veritas is one of the leading class society in terms of number of ships. And we are also a co-leader when it comes to flag delegation. 127 flag entrust us as a recognized organization. And when it comes to the gas market, we are currently working on more than 100 gas carriers to be delivered, and our class fleet comprises more than 340 vessels. So in this webinar, we'll have a look at the LPG and ammonia market, so the growth of this niche market. Then we'll have a look at the evolution of the ethane carrier design. Then we'll have a look at the carbon capture and storage project and the impact on liquid CO2 carrier segment. And then we'll have a look at the clean hydrogen shipping segment. And then we'll have a Q&A. So in terms of housekeeping rules, so we'll be very delighted to address your question at the end of this webinar. We'll have a 15-minute session. So please type your question in the Q&A box that you should see on the top corner of your screen. So we'll publish the answer and we'll answer them at the end of the session. And please rest assured your question will remain anonymous. So today's presentation is available as a PDF in the handout section, and you can find it in the handout section. So without further ado, I am very happy to give the floor to Carlos for the first session. Thank you, Carlos.
Thank you very much, Julian, for the introduction. I'm very pleased to be with all of you today to discuss this very innovative market of gas carriers. If there are two characteristics that can be mentioned in this slide for this gas segment, especially for ships that are not in the natural gas market, is the diversification in type of projects. And you will see 4 examples in today's webinar. And secondly, of course, the innovation, new ideas that are being considered to make these vessels more efficient and safer. So these are some details that are coming from statistics from Clarkson's about this diversification in number of ships and gross tonnage. So we can start the first section talking about the LPG and ammonia market. This is a market that has potential to grow further, and in particular the niche market of ammonia. In general, for the LPG, there are a key market highlights that we have to consider, especially in the last years. There was a change really significant in the size of the ships, the interest to transport the LPG or ethane as well from the US because of the production of shale gas, and these type of products are associated with the natural gas in the US. So this has changed the shape of the LPG industry. The tons per mile growth, the need for to have bigger ships, the impact into the trades of Panama Canal or the Red Sea passage. And these days, this is the main change in terms of export countries. In terms of market drivers, of course, we have to mention the diversification and the increase of petrochemical industry, in particular in Asia, in countries like China, also in India and in Southeast Asia. So the LPG trade basically now, considering that the US is becoming the leading export country, is shown in this map by BRS, May 2025, where you can see the volumes that have been exported mainly from the Gulf of Mexico, from the US to the Far East and to Europe. And of course, the second in ranking is still the Middle East, with also a significant amount of exports, most of them to the Far East. And the leading import country, of course, that is China. Then this reshaping of the LPG market has led to significant growth, in particular in the VLGC market, in the large gas carriers that are the biggest size so far for the transportation of propane, butane, etc. VLGC, which means basically very large gas carrier, and LGC, that is large gas carriers, are indicated in the table. There are ships over, in the case of VLGCs, typically over 80,000 cubic meters. In the case of large gas carriers, typically above 50,000 cubic meters. And we can see also that many of them, especially the last orders in the previous years, have been also dedicated to or at least prepare to transport ammonia. Of course, the small sizes are dedicated to petrochemical products, propylene, ethylene, as well as also propane, butane in small quantities for domestic trades are indicated here, for instance, with the handy size and small size. So if we see the ammonia market, if we zoom into this specific niche segment, this potential to grow is basically driven by the development of the blue and green ammonia terminals. There are many proposed. Some of them have taken already FID in the Middle East, in the US, and many other locations, Australia, even Latin America. So the new terminals that will produce this decarbonized blue or green ammonia will basically export these products to other parts of the globe, including, for instance, Europe in general, or the Far East, in particular countries like Japan, etc. The existing fleet of LPG carriers, even if we have said that is growing in terms of sizes, is not sufficient so far. And if the developments of this new decarbonized ammonia is taking place, there will be a need to develop bigger ships covering the transportation of these products. So we expect a booming market, and this has happened already in the ships that are in the range of 40 to 100,000 cubic meters. And the extra capex that is needed to build this LPG with ammonia capability to carry on ammonia is not significant. So this has been an advantage for many of the ship owners and shipyards to promote this type of products. Technology is well known. On the other hand, we can see here in this slide that basically for atmospheric type of tanks, the type A, has been used for many years in VLGCs, and in particular now the new generation of VLGCs and LGCs are using the type A tanks that you can see in the section here in this slide. And there might be also an option to use other technologies, but so far the predominant one is the type A. Membrane is mentioned here because it could be used, but so far there are no examples in the fleet. In terms of type of materials that we can use, low temperature steel, we mentioned two of the most common steels that are generally used. When we are talking about the ammonia carriers, we need to consider, of course, the extra additional cargo density of liquefied ammonia compared to LPG. So this is leading to a slightly additional draft and, of course, additional reinforcement for the tanks and for the supports of the tanks in general, or of the tanks. And these days, of course, the modern LPG carriers that transport also ammonia are prepared for full filling limits, not restricted, even if the density of the cargo is a bit higher. Of course, on top of the requirements of the IGC code, International Gas Code for liquefied gas transportation, we need to consider also in the technical design of the tanks and the structure of the ship, the US Coast Guard conditions. And in this case, of course, is much more important because these days the trade of LPG and potentially ammonia, blue in particular, or green ammonia in the future from the US might be very relevant. In terms of regulations, I think here what we have to highlight is that as of today, there is a new text of a revised text of the IGC code that is not yet fully approved or adopted because the full approval and the adoption has been postponed to 2026. In any case, this code that will enter into force in 2028, in July 2028, if the adoption takes place next year, at the end of next year, will include, of course, many new, I would say, modified regulations, updated regulations, including, for instance, the use of the other cargos as fuel, for instance, LPG and ethane. So this is a new development. It has been applied already. The use of LPG or ethane is not new in the gas segment, but now it's being formalized in the new version of the IGC code. There are also other regulatory developments in terms of IMO, which is, for instance, the use of LPG as fuel with the interim guidelines that have been used for a few years already and are already approved since 2024. And regarding the ammonia as a fuel developments, we need to highlight that in the IMO, there is an agreement already that in specific toxic cargos, in particular ammonia, can be used from July next year. There is already a regulation and one circular that is allowing this cargo as a fuel for LPG ammonia carriers. The only missing point in this part of the regulatory framework in the IMO is the development of a specific guidelines for the IGC code for gas carriers to use ammonia as a fuel. So the details of the safety aspect to use this cargo as a fuel is under development, and the expectation is that this guideline will be finalized ready next year. Next week, in particular, there is a subcommittee of the IMO that will address again all this regulatory framework, in particular the revision of the IGC code and the guidelines for the use of ammonia as a fuel. And on top of the safety part, we have, of course, all the environmental regulations that are impacting very heavily all the segments in general in the shipping market, and also in particular the gas carrier segment. And not only IMO, but also regulations, regional regulations, for instance, coming from the European Union. So a bit more detail about the transportation of the ammonia in the IGC code is detailed in paragraphs 14.4 and for the protection of the personnel on board because of the toxicity of this product, and also in chapter 17 specifically in order to reduce the potential corrosion of materials because of the ammonia corrosivity. Materials that cannot be used are described in 17.2.1, and in particular also very important materials for the cargo tanks and for cargo pipings, with some limitations to use steel alloys with nickel over 5% in percentage, or carbon manganese steel. So there are specific requirements, and of course there is also some kind of guidelines or circulars from the IMO to take in consideration when the tanks are defined. Another, I would say, very recent development in terms of regulations for ammonia is also the possibility to use in general for cryogenic cargos high manganese austenitic steel. This is something approved by the IMO, and in fact with several revisions of the circulars that allow the use of this austenitic steel with high manganese. And in fact, these materials might be a bit cheaper for cryogenic applications, even for temperatures lower than minus 55 degrees, which is the threshold that the IGC mentioned. But here we are talking about the specific requirements in terms of ammonia transportation only. And we have mentioned, and that's very important, the challenges regarding the environmental regulations. Here in the LPG segment in particular, is not new, the use of LPG alternative fuels that is already well known. Of course, there are still remaining challenges in this in the operation of the ships, but LPG as a fuel is one of the solutions that are considered. Ammonia as a fuel, of course, is becoming popular, but as we mentioned already in the previous slides, the regulatory framework is not 100% established. And the second challenge for the time being is the technology, because the engines are still under development. There are other alternatives also to use other clean or decarbonized fuels, but not only fuels, but also other technologies that we list in this slide. Of course, you may see that many of these new ideas or technologies that we present in the slide are not only applicable to gas carriers, but of course we also consider that are solutions technically proven that can be also applied, used in the designs of LPG carriers, like the shaft generators, PTOs, or with hybrid propulsion PTIs, with batteries, energy-saving systems, with waste heat recovery systems, wind-assisted propulsion. Wind-assisted propulsion in particular will become more popular for LPG carriers first, and then maybe other type of gas carriers. And we have to also mention the latest developments in Bureau Veritas, just to give a few examples of ships in the frame of LPG and or ammonia, in particular very large ammonia carriers under construction in Korea with ammonia prepared capability. An example by Naftobar under construction in Hanwha Ocean. Another example that have been already delivered, the mid-size ammonia prepared notation by Bureau Veritas in 2 ships already in service since 23-24, delivered by Hyundai Nippo in Korea. And on the right-hand side, very interesting to see the first example, the first ever example of a new build of an ammonia bunkering vessel, BB class. It was announced in the month of July this year. Sasaki design, Sasaki shipbuilder for Itochu as a ship owner. 5,000 cubic meters capacity, relatively small for the time being, because in fact the ammonia bunkering industry is still to be developed. And we have been supporting, of course, in the same areas in ammonia bunkering vessels with other designs with mainly Japanese and Chinese designers and shipbuilders. We have now one of the first polls. Yeah.
Yes, Carlos, and I will read it aloud. What are for you the most critical technical aspects when designing an LPG carrier able to transport ammonia? A, low greenhouse gas emission footprint. B, the design of the cargo containment system. C, the cargo as fuel system, including the engine, or any other solution. Please pose your choice. Thank you.
Thank you, Jose. So I will continue with the second section in just a few seconds. I think that the pool is more or less done. Quickly to answer, I guess. Okay, so LEG means basically liquefied ethane gas. In some cases, we can say also liquefied ethylene gas. But let's focus on the very large ethane carriers and ultra large ethane carriers. One example is this Matic design, very nice vessel and ultra large. It's a booming market because this ethane production, as we mentioned from the US, as a byproduct of the natural gas, is the amounts are relatively big, large. It's a relatively cheap product that can be easily liquefied in the US terminals, for instance, and transported into the crackers in the Far East, mainly as of today in India and China. China the first, second India, then other Southeast countries. Of course, there is a small production of from this ethane as a raw material. There is one first industry application, that is ethylene production. There are other applications, and you can see here basically the evolution of the US exports of ethane since 2014. That is really significant. And this is continually growing, and there are other terminals that will be developed in the US to transport this product. Of course, there are some challenges still today for the ethane trade between the US and the Far East. Still, the price is affordable. That's one of the main advantages, and this is why this is being used for cracking activities to produce ethylene, as compared to the naphtha or compared to the propane, for instance, to produce propylene. The ethane crackers, that they are developing and the development in China and in India, the capacity is growing with big companies there. But there are some challenges regarding geopolitics. There are, on one hand, some canal restrictions, tariff discussions. Of course, this is not finalized, but the US, as we know, is putting in place some commercial tariffs for imports into the US, and the other countries are doing the same for imports of the US products into China, for instance, or into other countries. The USTR is also something that may impact the fabrication of these gas carriers in China, but the real impact, the real effect of these geopolitical discussions for the time being is not something that we can forecast or we can predict easily. As we mentioned, the main importers are in the Far East. There are some cargoes going to European terminals, but basically these cargoes are being transported in medium-sized gas carriers, handy-size mainly, handy-size gas carriers, ethane carriers going to terminals in the UK, in the Netherlands, or Belgium. And now the trendy, but not recently, but already for quite a few years, the VLECs and potentially the ultra-large ethane carriers are very trendy. These are, again, ships that are over 90, most of them over 90,000 cubic meters, that are going basically to the countries in the Far East from the US. Technically, the ethane transportation is quite easy compared to, I would say, LNG. Temperature is minus 90 approx. You can transport this basically at atmospheric pressure. The density is a bit higher than LNG, and the type of product, according to the IMO code, is the 2G, similarly to the LNG. For the use of ethane as fuel, the only handicap here is the major handicap, I would say, is the density of the vapors. If you have a leak on the engine room, is slightly heavier than the air, and then this has to be considered when detection system, when ventilation system is designed. Flammable range is similar to the LNG, so there is no big issue on that from the technical point of view, because of course we have a lot of experience on LNG as fuel, and nowadays as well with ethane as fuel. In terms of technology for the cargo tanks, the main two technologies that have been used are membrane by GTT and Type B independent tanks with the insulation attached to the tanks. Both technologies are reliable, are proven for many years. Also in the frame of ethane, they have been used already in the LNG as well, primarily membrane in this moment, but in the past as well with LNG Type B. So there is no challenge in principle, and this slide is an illustration of the orders and the ships that are in service, information that is coming from GTT, one of the two designers of this type of cargo tanks, in particular the membrane, with the different projects that have been developed in shipyards in Korea and in China. With the membrane technology, basically the Mark III, with the Type B technology, and only one example with a Type C tank that is relatively big, but is something quite specific, and in principle, we will not see again in very large gas carriers. We have to highlight also that there has been one development that is important in the market, that is the membrane technology, in particular, not the previous one, not the Mark III that has been used typically for some of the very large ethane carriers already built, and some of them also still on order. But in fact, this technology was approved a long time ago by Bureau Veritas in 2014. But the new concepts that are developed this year are much more interesting, because they are tailor-made for very large ethane carriers or ultra-large ethane carriers for the transportation of, in principle, ethane, liquefied ethane, potentially also LPG. The main difference between these systems and the traditional Mark III and an NO96 is the thickness of the insulation that is reduced, and this is making the system easy to build, easy to fabricate, and at the end of the day cheaper for the shipyard. So we may see some of the examples in the future, some applications of these systems, of these slim systems of NO96 and Mark III in shipyards that are involved in ultra-large or very large ethane carriers. For the use of ethane as fuel, in fact, the first example of ethane as fuel was developed for a series of ships that are owned and operated by CPIC these days, and formerly Evergas, built in China, a series of 8 handy-size LNG, LEG, LPG carriers with engines by Wärtsilä that were, in fact, retrofitted at the end of the new building process in the shipyard to burn ethane instead of LNG. And the vessels have been in operation, are still in operation, transporting the ethane from the US to North Europe and burning ethane as fuel with a specific Type C tanks on deck for this fuel. Of course, on top of this technology that is already and was the first technology approved for ethane as fuel, we have the engines that are running for a few years already with gas injection, with high pressure gas injection, that is the MAN, or better to say now, Everlens, that is the new brand, the new name of the company, that are similar to the LNG two-stroke dual fuel, but with gas injection that is even higher than natural gas injection. And just to finalize a bit with some references of Bureau Veritas experience, on top of all the previous experience on handy size, with ships that are in the range of 20 to 30,000 cubic meters, typically equipped with Type C tanks, we have a very good reference now with 5 100,000 cubic meters BLECs under construction in China for a company called SP Chemicals. That is a design by Marek with 8 Type B prismatic cargo containment tanks. So basically there are 4 tanks, but divided in the middle with a longitudinal wash bullhead, will be equipped, of course, with the MAN Everlens dual fuel ethane engines, two-stroke engines, and they are capable of transiting through the Panama Canal. We have, of course, other examples, approval in principle, with mainly companies in Korea and Japan, sorry, in Korea and China, also including ultra-large ethane carriers. Good, and I give the floor to Jose again. Thank you.
Yes, we have a second poll for the audience. In your opinion, in terms of cargo capacity and containment system, the majority of new generation very large ethane carriers or ultra-large ethane carriers would be either larger than 100,000 cubic meters and equipped with Type B tanks, larger than 100,000 cubic meters and equipped with membrane tanks, or otherwise smaller than 100,000 cubic meters with Type B tanks, or smaller than 100,000 cubic meters with membrane tanks, or a combination of different sizes and cargo technologies without any prevailing tendency. If you can please make your choice.
Thank you, Jose. Thank you, Jose, for the poll. And then we are switching into another segment. Basically, I have the pleasure to give the floor to Benoit. Thank you.
Thank you, Carlos. Can you hear me well?
Yes, loud and clear.
Yes, very good. Thank you. So my pleasure to be here for these two other topics, which are CO2 and then we'll see after hydrogen. And then the CO2 carriers we'll go to see are really linked to the carbon capture storage project, where we can see that this activity is growing with many more projects arriving. So here you can see on the map, Northern Europe, the list of the different projects. The color would indicate the status of the project, either they are already developed in development or are just speculative. And then linked to this project, we have the number of vessels. So the table on the left will show you in black the existing vessel. So we all know that CO2 vessels historically have been used for food transportation, and then these 4 vessels in service for quite some time, small capacity. And then in blue, we'll see the recent deliveries. So the 2 Chinese-Japanese projects, which are more prototype in terms of development. And then the famous, of course, Northern Light project with the 2 vessels in service. And last week, Northern Light announced that they successfully stored their first CO2. So this project is now up and running. Then in dark blue, we'll see the 3 new vessels, so 2 attached for Northern Light, and 1 new project that will arrive on steering quite soon, which is the Green Sun project, with 1 vessel currently under fermentation. So you can see that we have mentioned LP, MP, EP. So LP is low pressure, MP is medium pressure, EP is elevated pressure. That's the 3 possibilities for transportation of CO2. If we go into existing rules and regulation, today, what do we have? So IGC code is covering CO2, and there is a specific requirement, Chapter 17. And of course, the class rule and the BV rule are already covering CO2. But there was a bit of update in the IGC code, mainly based on the work from CITCO and ISO, and with a new revision of the IGC code to include clarification on the triple point and the toxic categorization. So in terms of industry guideline, CITCO, ISO, CITCO has released a first carbon dioxide cargo and gas carrier, which is an operational guideline, with different actors of the industry joining together to try to address the most probable operating condition. And then ISO has released also last year, TR, a technical report on transportation of CO2 by ship. These 2 groups, ISO and CITCO, are still working to develop some further guidelines, taking advantage on the first experience in these first 2 projects. Then, of course, we cannot talk CO2 without showing a phase temperature diagram. So particularity of CO2, triple point, which is very high, so that we cannot transport CO2 in atmospheric pressure if we want to have it liquid. So we need to be above the triple point, so above something like 5 to 6 bar, depending on the temperature. The green line will show the low pressure range, so around 6 minus 50 degree, 6 bar minus 50 degree. The yellow orange line will show the medium pressure, where we are in the minus 30 degree and the 15, 18 bar. The challenges with this low temperature and this quite elevated pressure is, of course, the material selection. So material selection is covered by the IGC code. So in the IGC code, we have the 6.2, the table 6.2, that will restrict yield strengths, impose some temperature design if we go below minus 10 degree, and then some additional treatments such as post-welding treatment and so on. Alternative material can be developed, and there is an MSC guideline. And then the table on the right showing the different classical material, the nickel steel particularly known to be okay for low temperature. And then the yellow, blue, and green are the specific material. The P690QL2, which is quite famous to have been qualified for Northern Light, as an example. The P355, which is a more classical material, and the F550, which is a specially developed material by a European steel maker, which has good capacity in toughness at low temperature. And then I mentioned also manganese steel, which is also quite famous in the application, also on LNG transportation. Main challenges, of course, we have the toxicity. So revision of the IGC code to cover this toxicity. So you will tell me, yeah, but CO2 is also in the exhaled air. Yes, the concentration we have in the exhaled air around 4%. And this is something we see, which is something like above this percentage, we start to be toxic. What's the consequences of that? Gas detection. So not only CO2, not only oxygen depletion, but CO2 concentration in some particular area, such as the accommodation entrances and some few requirements on gas dispersion. Of course, the impurities, this is a very famous topic. The problem is CO2 is coming from different streams. So depending on the capture technology, we may have different impurities. The risk of impurities is acidic formation, so corrosion, and then also an impact on the phase temperature diagram, which may create some issue on the condition, on the transportation condition. So Northern Light, for example, has updated their specification last year or 2 years ago, and ISO and different working groups are working into different CO2 specification, depending on the need. The ISO specification is linked to the pipeline transportation. And of course, the depressurization is the famous topic. So the fact is, during depressurization, CO2 will go in very cold temperature, around minus 78.5. So it will create brittle condition for the metal, for the pressure containing part. And dry ice formation, the risk would be, in case of depressurization, we can have blockage in the ground. So, of course, BV has been working a lot on different topics. So, of course, tanks design, ships design, and material, as said, which is a very particular topic. Of course, on the two famous one, which is the P690, with different tank manufacturer to qualify welding procedures. And then the voestalpine, the new F550 TMCP tough core with very good characteristics. And of course, BV, it's an important topic for us, this CO2 vessel for Green Sun project that should be soon delivered, which is under construction. I think we will have a poll. So which type of cargo condition do you think would be prevail in LCO2 carriers below 20,000 cubes capacity? So either low pressure, which is around 6 bar minus 50 degree, a medium pressure around 18 bar and minus 21 degree, or an elevated pressure 40 bar and 5 degree. Other. Okay, thank you. Then let's now switch to liquid hydrogen transportation supporting clean hydrogen shipping. Where we are today, we see a lot of development projects on green corridors, hydrogen transportation to transport green energy between the different locations. And we see on this map, hydrogen council, potential project and potential development. Some hurdles on this one, as the example on the top left, which is that showing that Shell has finally backed up on one of their projects. So some challenges in developing this different hydrogen project. So why? Because hydrogen transportation is quite critical. Why? Cryogenic temperature. We need to transport hydrogen in liquefied condition. We need to go down to minus 253 degrees. Very high pressure if we want to go into pressurized condition, above 350 up to 700 bar. And then, of course, this large range of flammability, as can be seen on the graph, which is showing hydrogen flammability range compared to other classical gases such as methanol, ammonia, and methane. So challenges in this design. Today, hydrogen is kind of covered in the IGC code, but not specifically. And even if we have a table to cover that, it's linked to an interim recommendation. We'll see that later. For the condition for transportation, so let's have a look at the phase temperature diagram. We see the triple point is quite low. And then we need to be in this liquid phase, which is giving a quite small range in terms of temperature and pressure. So if we go in type C transportation, we need vacuum insulation to keep it very cold, because even if we go up to 5 bar, the temperature range would be quite limited. So for large ship specific developments, mainly on type B or membrane vessel, with this range of temperature very limited and quite similar to LNG in terms of pressure. Rules and standard, as we said, IGC code not fully covered. So there is an interim guideline which was first released in 2016 and which has been revised and adopted at the 108 committee, which is the MSC 565. So this could refer also as a gas transportation vessel to SOLAS, FSS code, and the IGC code. But this MSC guideline would also refer to some standards, particularly in terms of material selection and qualification, fire detections, and things like that. Significant projects developed, so a lot of JDP and AIP, and we are particularly proud of this project, which involved a lot of actors, development of a 150,000 cube vessel design with GTT and Marine as a designer, which was already published some time ago. But you can see that a lot of different designs have been developed also.
And we have a couple of polls before we move into questions and answers. First one is which carrier segment, other than LNG carriers, do you see expanding faster in the next years? LPG carriers able to transport ammonia, very large ethane carriers or ultra large ethane carriers, liquefied CO2 carriers, or liquefied hydrogen carriers? Please make your choice. And there is a second poll that will come out in a moment. And I will leave you for the questions and answers. The last poll, up to 2035, which will be the predominant technology to achieve the lowest greenhouse gas footprint for gas carriers other than LNG carriers? A, the use of cargo as fuel, the use of other alternative fuels like biodiesel or biogas, wind propulsion, or a combination of other technologies such as shaft generators, air lubrication systems, and energy-saving devices. If you can please make your choice. Thank you.
Okay, thank you very much. So now we will move on to the question and answer. So please don't hesitate to type in your question in the Q&A box. So we have already a couple of questions that have been asked. So I will start with the published one. This one will go for Carlos. It's about cargo pumps. The question read like this: which type of cargo pumps are mainly used, recommended for ammonia carrier? And what is the material that is used for cargo pumps and piping system? Carlos, you okay with this one?
Well, yes, thank you,
Okay.
Julian. Thank you for the question, Fulvio. Well, in fact, the LPG carriers generally are equipped with deep well pumps. So typically the electrical or hydraulical motor is on the top of the tank, outside the tank, of the cargo tank, and then you have the piping going down to the deep well. This is the reason for the name. For the ammonia carriers in particular, the type of pump will be basically the same, deep well tank, but of course the materials will have to be aligned with the requirements, the specific requirements of the ammonia to prevent problems with the corrosion, and also the question that you are asking is related to the cargo piping. So the same type of requirements that are indicated in the IGC code have to be considered in the cargo piping, and also other materials that will be, for instance, used in the gaskets or in valves, etc., etc. So all these requirements regarding the prohibition to use copper, alloys, nickel, etc., etc. So this is the main difference compared to a pure LPG carrier. Thank you.
Thank you very much, Carlos. So now there is a question on dry inert gas system. Benoit, you are happy with this? Or for ammonia and ethane carrier, what is the recommendation for dry inert gas system? Would it be combustible type or PSA N2 membrane type needed? Or it's a bit too technical?
Yeah, it's okay. It's a bit technical. So that the question is linked to ammonia carrier. Huh? So,
Ammonia and ethane carrier, what is the recommendation for the dry inert gas system? Yeah.
So ammonia, we know the issue of carbamate. So that's the question in the inert gas system. You should not mix the ammonia and CO2 because we're going to. So you need really a good purging of the ammonia. And then I would say in terms of ammonia, we have already quite a good experience in inerting. So the LPG guideline can be used. Ethane, similarly, I would say definitely for this type of vessel, we go into the economical balance between nitrogen generator and the gas generator with high purity. So yeah, definitely we need high purity system.
Okay. Thank you. I keep you, Benoit. There is a question on liquid CO2 carrier on the ventilation of the tank with dry air in relation to tank inspection or dry dock. Any requirement on ventilation?
So yeah, CO2 is an interesting question. So CO2, the problem of CO2 is you want to avoid the dry ice formation. So I would say that going into dry dock is less stringent than coming back into service. Putting back into service, you really to avoid any water formation. So we know the water impact on the CO2 will lead to this acidic formation. So we want to have really dry formation, and of course to avoid the dry ice, and to avoid ice coming also from the water. We want to avoid the humidity, and we want to avoid the corrosion. So the purity is quite important for putting back in process. That's for sure.
Okay, thank you. Then I have one for Carlos, which is a bit controversial on elevated pressure. So if we have any view within BV on the elevated pressure shipping ID, and I think it's more general for all type of gas carrier.
Yeah, that's a very specific one, very, of course, very relevant because it's one of the three technologies that is being proposed. So far, according to the developments, is not the, I would say, the one that is being proposed in the projects for small or medium-sized ships. And I mean, it's technology that is proven, but in fact, the main advantage here is that you increase the pressure and you can transport at atmospheric temperature. The complexity is that you have many cylinders on board. So basically, you transport a lot of small cargo containment systems as compared to, for instance, low pressure concept or even medium pressure concept. There is only one company, in fact, that is involved in this type of concept, elevated pressure. That is Knudsen NYK, a company that in fact is a joint development between the two and is called NKCC. So for the time being, we see that is, of course, there is some room for the technology, but our feeling is that is running a little bit, at least a little bit behind than the other two, because we have examples of vessels already built, delivered, at least a few delivered with medium pressure, and also a few others that have been built by Korean shipyard 22,000 with the low pressure technology. So this is the main thing. Technically can be proven, but there are no examples yet. Okay, thank you.
Okay. Thank you, Carlos. Benoit, there are some questions on purity of LCO2. Actually, there is two questions. Maybe I will merge in one. They say that for the transportation of CO2 in large volume, does BV see market imposing relatively cheaper restriction on upstream treatment to force high purity of LCO2? Question from Thomas. And I have another one, which is which type of LCO2 is assumed to be transported by ship? A high purity only or wet LCO2, highly corrosive as well? I mean, there is a so it's a
combined question.
Yeah,
that's the hot topic in the industry. The purity question is really a hot topic. Shipping has never defined the specification of a product to be transported. Shipping is always a service, so we don't see shipping imposing a condition, because we should be able to accommodate vessel able to transport different types of purity, except for the corrosivity aspect. If we have highly wet CO2, if we call it that way, so a lot of water formation and then a lot of acid, then we'll have high corrosion rate in the tanks, and then it's destroying the vessel. And then protective coating at minus 40 degrees, it's very challenging. So today, this is, avoid the water formation, avoid the acidic formation. That's. Then in terms of purities, the issue is to take purity, a certain quality from one side, to discharge, then the impurities will stay in the vapor phase, and then you will bring it back to the next customer. And then there is a question of how customers can accept different purities if there is a kind of milking run scenario for a vessel. So it's a question which is not only on shipping, which is between the different emitters. So shipping will not push for specification on CO2. It will be more the emitters that will push. That's my personal feeling. Some people would like shipping to impose it,
Mm.
but shipping has never imposed it.
Yeah, we do our job. Thank you very much for this answer. Then I have a question for Carlos on the boil-off gas and hydrogen transportation. Is it a challenge and a concern, although it might be of importance and that can destroy the economics of the cargo and transportation for medium and large distance? Are you able to elaborate on the topic of hydrogen boil-off gas? Yeah.
Yeah, indeed. This is the one of the main problems here because, of course, the temperature for transportation is quite low. As we have seen, the efficiency of the containment systems is evolving. We have seen in LNG carriers, for instance, that of course the thickness and the characteristics of the foam of the insulation are better than before. So the boil-off rate, for instance, for a big cargo tank on LNG is half of the previous boil-off rate a few years ago. But in fact, in the hydrogen, the main handicap here also is that when you have this amount of boil-off gas from the cargo tank, as of today, there are just few technologies that are available, very, very few, that are available to use, for instance, the hydrogen as a fuel. A fuel cell, for instance, and a very limited amount of engines. In fact, maybe just 2 or 3 that can use hydrogen. There have been testing also of engines combining LNG vapors, of course, natural gas as a fuel with hydrogen. So this might be also one potential use if you have hydrogen on board. But I think there will be an evolution of containment. We have seen one of the projects approved that is a very large hydrogen carriers, 150,000 cubic meters with membrane, vacuum insulation, etc. Of course, you always have a chance to have the gas combustion unit on board. And normally, the vessels will be equipped with this to manage the boil-off. Because reliquefaction will be quite difficult and expensive on board. And then, yes, I think the question is very relevant because commercially, at the end of the day, maybe is in some cases is not feasible, is not interesting to develop the project. If in case you have to burn the cargo, basically a big part of the cargo in the gas combustion unit, and you are not and you don't deliver the amount of cargo that you expect. So this is one of the handicaps that technically can be solved, but it will cost money at the end of the day, and there will be a kind of balance between the required capex on board, development of new technologies to handle this boil-off gas, etc.
So we'll have to wait for more development here, but thank you very much, Carlos.
Yeah.
Then we have a question, maybe Benoit can take it, on PP, personal protective equipment, medical response requirement when it comes to a low temperature cargo. What are the requirements in terms of PPE?
Yeah, that's a very good point, because we look at gas transportation. Always we have this view on explosivity and so on, but the low aspect is very important, and the cryogenic burn is really an hazard. So IGC code has some requirements on some of the protective equipment to be carried out and to be worn, particularly in all the transfer parts. So manifold area, we have cryogenic protection, but you need a glove, full face shield, and so on and so on. Additional to the protection of equipment, there is the protection of personnel. So IGC code is a statutory requirement then that we do as a delegated to the flag. But we look also into the PPE and be sure that the equipments are there, even if we are entering them into the ISM part. And then, of course, STCW has a specific qualification for crew operating a gas carrier, and which by extension went also into the IGF. So that's the STCW qualification for IGF. For the crew to be aware on this cryogenic burns and low temperature things. And of course, we can go to SICTO has published this liquefied gas handling principle, well, you have a lot of requirements, particularly.
Okay, thank you very much for this detailed answer. So there are a lot of questions that are still unanswered, so we'll answer individually to each and every one of you. So with that, we have reached the end of our webinar. So I would like to thank you for your attendance. I would like obviously to thank our speakers for sharing all this information on gas carrier segment. The recording will be available on our Bureau Veritas website. Again, the handout is available in the handout section. So with that, I wish you a good continuation of the day and thank you very much.
Okay.